the phased array stuff that's in there that Llewellyn did, it will work, but if you get it tuned up, you're lucky. It'll take you probably $20,000 or $30,000 worth of test equipment to get it tuned correctly. And even if you do get it tuned, it will only hold its pattern over a few tens of kilohertz, if that. So the advantage of using the C-match method is that it holds its pattern over the entire band instead of just about 10 or 20 kilohertz. So anyway, I've got all the principles and background in the book, and there's also a CD in there with an Excel program that you can load up, and it'll do a 2-element array, and it'll do a 4-square in the Excel spreadsheet. So you can get in there and play with patterns and play with phasing and play with power distribution between the antennas and see what happens. But the big problem with phased arrays, particularly if you're not running, if you're just running a linear array where there's 2 verticals or 4 verticals in a line, is that your amplitudes to the antennas have to be equal. And getting them equal when the base impedances are completely different because of the mutual coupling between the antennas is not an easy thing. And if you don't get those powers equal, then your nulls don't form. And so the nulls don't form, you don't have anything but a poor vertical instead of a phased array. The 4-square is easier to do because it's much more forgiving. The 4-square, because of its geometry, allows you to mismatch your power between the verticals by quite a little bit before the pattern's really affected. So anyway, that's probably more than you wanted to know, but that's one of the reasons I did the book, was because the other methods that are out there, if they work, will only work over a very limited bandwidth, and then the whole thing falls apart, and you'd have to retune it again, which is difficult. So anyway, yep, they're fun when they do work, and they do put out a pretty decent signal. And with your radial system, you won't have any trouble. You only need 15 radials rather to be about 86% efficient, and beyond that, up to about 60 radials, you'll gain maybe 3% more efficiency, and that's about it. Beyond 60, there's no advantage. The reason they make broadcast stations put down 120 is because they know that over time those radials are going to break, and they want to make sure that there's enough of them down there that the feed point impedances of the towers don't change, and so the patterns that are set up are not affected. So anyway, there you have it.
KC9VKV.
Who's the KC9?
Kilo Charlie 9 Victor Kilo Victor. This is Jim around Louisville. Just copying the mail on the QSO there, and curious, what is the name of your book?
It's called the C-match method of phasing vertical antennas.
Where might that be available?
Universal Radio has it in Ohio.
Roger, Roger. And what would you say the practical gain differential of a phased array might be over, say, a horizontal dipole?
Well, that's a discussion that takes about half an hour, and I don't have that. But basically, if you want to get a the same kind of signal into Europe, say, your horizontal dipole is going to have to be on the order of a half wavelength in the air relative to what you can do with ground-mounted vertical. Over.
Roger, and you're talking about basically two vertical entities to make an array, or four, or how many?
Well, gain goes up with the number of elements, of course, just like with any other kind of antenna. But a two-element phased array, and again, you have to look at what's going on in the vertical pattern as well as the horizontal pattern. The vertical pattern of a phased array has got a lower radiation angle if your ground system is good. That's the whole key, is you've got to get a good ground out there, good radial system, because that pulls your vertical angle down, and you want your elevation takeoff angle to be somewhere around 10 degrees. And with the horizontal dipole, you don't get that kind of concentration of low radiation angle unless the antenna is fairly high. And so the forward gain on the phased array is mathematically about between 3 and 5 dB. It doesn't look like much, but the real purpose of phased arrays is to get rid of interference from bad directions, and that's why broadcasters use it, is because you can carefully steer the nulls of the pattern to point them at other stations so that you don't interfere. And so the phasing, the spacing, and the power balance between the antennas actually controls where the nulls are and how deep the nulls are. And because you're putting nulls into part of the pattern, the energy that would have gone into where the nulls are goes into the major lobe, and that's where the gain comes from. So long story short is, theoretically you get 3 to 5 dB gain with two verticals, but in reality, because the angle of radiation is so low, it's a great DX antenna, which performs far better than dipoles do, unless the dipoles are quite high. So I don't know if that helps or not. KC9VKV is it? And what's the name and where you at? K7 November Mike, over.
Roger, Roger. The name is Jim, Juliet India Mike, and we are located near Louisville, Kentucky, just across the river from Louisville on the Indiana side, about 3 miles west of Louisville. We can see downtown. So this phased array on the vertical side, you would be dedicating that array to a specific directionality, Roger?
Well, yeah, in its simplest form, you could do. You could make it switchable, and I talk about that in the book of how to do that. You need some relays and some additional capacitors and so forth in the tuning part of it. But anyway, what I've done with mine, just because I'm a simplistic person, is I tune it up and have it one direction, like east, and then if I get excited about talking to the JAs, I'll go out and retune it for west, and so that's one way of doing it. It takes about 20 or 30 minutes to retune it, but one direction is okay with me for a while, but there is a way to make it switchable over.
Roger, and let's see, your vertical antenna configuration, is that what you would find in AM broadcasting with ground radios, etc., Roger?
Yeah, that's use of it, and so, vertical doesn't work without a ground plane, no matter what people tell you or what the advertisements say. You have to have a ground plane or some other form of counterpoise to make it a vertical dipole in order for it to work. So, anyway, you need about 15 radials to make it about as effective as it's going to be. Anything more than that is just insurance. You might pick up another 1 or 2% of ground efficiency, but according to all the studies that I've read, there's a really good study that was done by the proceedings, I think, of the IRE or something like that back in the 70s, where a guy went out and did a bunch of studies on broadcast stations, and they found that 15 radials is the minimum you need for an efficient vertical, and then beyond that you only gain a couple of percentage in efficiency, all the way up to 60, and beyond 60 you really don't gain anything more. So anyway, that's kind of a rundown there, Jim.
Roger, I was just also curious about your retuning speed. Is that because of your technique of tuning or in design?
Well, it's a long story. When you change your phase angle of the feed point, lots of things play at the same time. Probably the biggest thing that happens is that between the phase of the opposite antenna coupling into the first antenna, if you're just doing a 2-element array, and it's true with all of them, if you got more elements than 2, it just compounds the issue. But the phase of the RF that's coupling back from the first antenna to the second antenna, and its phase angle will modify considerably the base impedance of the first antenna, and then of course the field from the first antenna coupling into the second antenna modifies the feed point impedance of the second antenna. And the reason that that's an issue is because with the reactive components and different resistive components of those base impedances, you have to be able to match those correctly and at the same time distribute the power equally between those two antennas, because if you don't get the power equal, then the nulls won't form. Over.
Roger that. And so I'm just curious because in broadcast it takes days to get phase angles and power relationships correct for the correct pattern to protect whatever areas you are, and to be able to retune in half an hour is really amazing.
Yeah, you're exactly right. And not only that, in the broadcast world, you've got operational impedance meters that are in line, so you can see what you're doing, and the average ham can't begin to afford those things. And plus, you've got a field strength meter that is calibrated, and the average ham can't afford one of those things either. And then once you get the whole broadcast array tuned up, it's only good for maybe 20 kilohertz, and beyond that, it falls apart. And most hams don't operate in 20 kilohertz.
Roger. So how broad would you say your bandpass would be?
Oh, it's the entire band.
Amazing. And but as you move out from the center frequency, your SWR, does it go up, Roger?
No. It doesn't, and for several reasons. First of all, the antennas I make out of 3-inch diameter aluminum irrigation pipe, and the wider the diameter, the wider the bandwidth and the lower the Q of the antenna. So the Q of the antenna is around a 1 or a 2, And secondly, the way that it's done is with transmission line theory, and as you move off the center frequency, and it's a long story, but what you do is you make the antennas too tall, so that the base impedances are always reactive on the positive side, so they're inductive. Even with the mutual capacitance between the towers or between the antennas, you have to have them tall enough so that the base impedances are a positive J or positive reactance. And then you put a split capacitor at the base of each antenna, which you can do a Q transformation of the positive J factor so that it looks like a parallel coil to the capacitors. And then you tune up the capacitors so that it basically resonates that positive J factor, so it's a parallel tuned circuit if you want to look at it that way. And then you use the split capacitor to match impedance. So you feed your coaxial transmission lines in at the split of the capacitors. And so when you tune up the verticals and adjust them for equal power and minimum SWR simultaneously, so you need 2 SWR bridges at the base of each antenna, and you drive it with 10 watts or 15 watts, something that's manageable. And you go back and forth and tune the capacitors for equal power and minimum SWR. And the whole system is broadbanded enough that what happens is when you get those capacitors in resonance, then your phase angle across the capacitors in conjunction with the inductance and the verticals has a 0 phase angle, because that's the definition of resonance. And so the two phases from the matching networks are 0. And then as you move off frequency, those tuned circuits do detune, but the phase angles of the tuning track each other within a few degrees. And what's important is that the contributions of the matching networks track each other. It doesn't matter that they are different, but as long as the phase doesn't upset itself, and as long as the power distribution stays relatively constant, then the pattern stays in place, and that's how you can get it across the whole band, if that makes sense. Over.
Oh, Roger. Yeah, we're having some little fading conditions, but just curious. So essentially, what you have is 2 variable capacitors at the base of each antenna, and then your SWR bridges. You have a circuit that you can insert those and do your tuning, and then take those out, Roger?
Yep, that's the way you do it. It's just put them in, tune it up, take them out, and that's it. Gotta go, Jim. I've got to go to work. Sorry I can't sit more, but I have to do this another time. KC9VKV, K7NM.
Roger. What's the name there?
My name's Lee, London Echo Echo. I'm located near Salt Lake City. Over.
Roger, Lee. This is Jim here, and we do have a YouTube page where I celebrate 50 years of commercial broadcasting, and we've just started a new segment about 8 months ago called QSO-VLOG, which is dedicated to all areas of amateur radio, and essentially what that is air checks that we post, and I'll probably be posting this conversation and again, and because of that, I'd like for you to repeat again the name of your book and where it might be available.
Yeah, just a second.
This is Kilo Charlie 9, Victor, Kilo Victor.
Yeah, it's called the C-match method of phasing vertical antennas, and it's available at Universal Radio. And yeah, I did give a forum on this at Dayton in 2006, I think it was. Might have been 2005, can't remember now. And then again at Visalia the following year. So anyway, that's the story there, Jim, over.
Roger, Roger, Lee. Well, we'll be posting this on YouTube. If you go to YouTube and do a call letter search, Kilo Charlie 9 Victor Kilo Victor, that will take you to roughly 90 QSO-VLOGs that we've done in the past 8 months or so. And right at the top of that page, there'll be a list program which has all of them in there. And right at the top of that list is Art Bell, and then the rest are sequential below that. And this one will probably be up there towards the top, right below Art Bell. So again, it's Kilo Charlie 9 Victor Kilo Victor as a search on YouTube. Roger, Roger.
Yeah, okay, Jim. Very good. Well, I appreciate that, and very interesting. I'll have to check that out for sure. Okay, well, thanks a lot for dropping in, and nice conversation, and we'll hope to catch you down the log, and we'll take a look at the YouTube there. KC9VKV, K7NM, 73.
Roger, Roger, Lee. Just at the nick of time. I think we just about lost condition. So 3's your way. Have a good day, and we've enjoyed it immensely, and we'll catch you later. This is Kilo Charlie 9, Victor Kilo Victor. We'll be clear.